We just talked about nomenclature of binary molecular compounds and different carbon, hydrogen, and oxygen containing compounds and groups within them. Now let's talk about the properties of molecular compounds and how they relate to the structures of the compounds. So they can be gas, liquid, or solid at room temperature. They tend to have low melting points, low boiling point, and low electrical conductivity. And so first thing is compared to what? So compared to metals and ionic compounds. So in metals, there are metal atoms that are the main interacting feature, and ionic compounds have ions. So contrary to that, these have molecules as their main particles, let's say. And when molecules interact, let's look at something like carbon dioxide or H2O or methane, CH4. So these compounds and covalent compounds in general will have low electrical conductivity because the electrons will be bound up in the bonds and the atoms. They will not be free to move. They have low melting and low boiling points, we'll see when we talk about intermolecular forces, because the forces between one CO2 and another, or one CO2 and an H2O, are relatively weak. Okay, we'll talk more about what those forces are, but you should know that they have low melting and boiling points and low electrical conductivity when they're molecular compounds. Now let's talk about hydrated ionic compounds, and specifically a little bit about what they are and how to name them. I have an example here. This is a calcium sulfate dot 2H2O. That is typically how they're noted. And the dot H2O means that in the solid structure of calcium sulfate, there are two waters that get trapped between the layers of the ionic compound molecules. And so that they basically get trapped due to the strong ionic forces that are pulling the H2O molecules into the structure or not allowing them to escape. Of course, we can get them to leave by heating, and depending upon how much heat we apply, you can get some or all of the waters to leave. These are called waters of hydration, and the name of this is going to be calcium sulfate dihydrate. Calcium sulfate dihydrate, where dihydrate is one word. And the number prefixes we learned for binary molecular compounds totally work for these as well. Only thing is there's an additional one when I wrote hemi before. It speaks only for hydrates. This is going to be calcium sulfate hemihydrate. And this would not be a good way of writing the balanced reaction because it does have a fraction in it. Fractions should be cleared in balanced reactions. Now, so the only difference between these two compounds is the number of waters that are trapped between the calcium sulfate layers. This one, gypsum, that's going to be the common name for calcium sulfate dihydrate. Heat it, you can turn that into plaster of Paris. And each of these has slightly different properties based on the number of waters of hydration in them. Hydrated compounds are actually relatively common. I'm showing a picture here of cupric sulfate, which is also copper 2 sulfate. It is very bright blue, and it has 5 waters of hydration. So the name of This compound here would be copper 2 sulfate pentahydrate. Where we've got the Roman numeral in capital Roman numeral letters and in parentheses. Sure enough, if you heat that, you get copper 2 sulfate, and sometimes called, just to distinguish it from its hydrate version, or the multiple hydrate versions that are possible, it's also called copper sulfate anhydrous. Meaning no waters, dry is another way of saying that. Epsom salts, after a long day of standing at the board back in the day when we met face to face, I would sometimes come home and dip my feet in a solution of Epsom salts. That will be magnesium sulfate with 7 waters of hydration, also known as magnesium sulfate heptahydrate. And there are lots of other examples, but these are 3 that I wanted to include.